Good morning, good afternoon, everyone. I appreciate everyone's time in joining us today. My name is Al Rivera. I'm with Baltimore Air Coil Company. I'm an account manager with our commercial refrigeration group. So I spend a lot of time talking with end users, consultants, engineers, and contractors about condensers, fluid coolers, and cooling towers. And so today, my goal is just to highlight what some of those options might look like for you. Here's a quick overview of the topics that I will cover. A brief discussion about transcritical versus subcritical operation and how your choice in heat rejection can directly impact that. Quick overview on the different condenser options that are available, being air-cooled, adiabatic, and evaporative. Then I will highlight, to the best of my knowledge, what all the available options are based on your choice in refrigerant. Then we'll segue into hybrid fluid cooling and water-cooled systems. Spend most of my time talking about adiabatic cooling, how adiabatic cooling works, what are some of the pros and cons versus air-cooled and evaporative cooling. Then last, talk about water and energy use with each of these types of technologies and what the trade-off is between the two. And then leave plenty of time at the end to address any questions or hopefully have a discussion. So let's get into it. Until recently, we never really had to have this discussion about transcritical and subcritical refrigeration operation. And that's because our legacy HFC refrigerant systems always worked in subcritical mode. The critical temperature or the critical point being at which above we cannot condense the refrigerant, and below the critical temperature, we can have all three phases exist. So for example, with our 134A refrigerant, the critical temperature is nearly 214 degrees. So we're always going to be condensing below that. So the system is always going to be running subcritically. If we contrast that with the physical properties of CO2, the critical temperature is just under 88 degrees. So that's a temperature that we see very commonly all across the US. And so this critical versus subcritical operation becomes part of the conversation. We're operating subcritically when our condensing temperature or our leaving gas temperature is below that critical temperature. And what's important is that a subcritical fluid can reject heat by actually changing phase, by condensing. Above the critical temperature, we can only reduce the temperature of that fluid. And that's where we get the terminology of a gas cooler when we talk about transcritical CO2 systems, because we're only able to reduce the temperature of the vapor CO2 going through the gas cooler. But if our system is operating subcritically, then our gas cooler actually becomes a CO2 condenser, and we can condense the CO2 from vapor to liquid phase. If we take a look at the refrigeration system plotted out, we have the subcritical operation in the lighter blue and the transcritical in darker blue. So as I mentioned, in the condensing phase, we can see much more heat is rejected through the subcritical operation compared to the transcritical. We also see much more enthalpy or capacity available at the evaporator for subcritical versus transcritical. And then last, much less compressor work is required for subcritical operation. So let's take a look at what that would look like in terms of some equipment selections and some numbers. So here we have a CO2 refrigeration system, the same evaporator load for both, 700 MBH, ambient design conditions of 100 degrees dry bulb, 69 wet bulb. That's a pretty dry climate, probably something like Northern California. If using an air-cooled condenser or gas cooler, we're going to be limited by the ambient dry bulb temperature. So our design has to consider what the ambient temperature allows us. So in this case, we're going to use a 4-degree approach, which means that our design outlet gas temperature on a design day is going to be 104 degrees. If we contrast that to using an adiabatic type of product where we're going to use water to enhance the cooling capacity, we're no longer tied to this dry bulb temperature, and that allows us to design an outlet temperature much below what the ambient dry bulb temperature provides, in this case, 80 degrees. And what the results are: much lower system pressures, much lower compressor power is required. And in many cases, actually less compressors or smaller compressors could be used. We get much more efficient compressor operation. And again, we see that the total heat of rejection that's needed is actually less when running and designing a subcritical system. So now we're going to jump into what the main condenser options are and discuss the pros and cons of each. So air-cooled is the most common. It's a relatively simple and familiar piece of equipment. Most HVAC and refrigeration technicians are going to be very comfortable working and maintaining this piece of equipment. So for that reason, it has relatively low maintenance requirements compared to the other options. There's no water used at the site, and they typically are the lowest first cost option available. Opportunities for improvements or things that could be better: they have the highest condensing temperatures, which means that they're going to have the highest energy usage of the options. And since we're reliant only on the dry bulb temperature for cooling, that typically means we need a large surface area in the cooler, in the coil, in order to make that capacity. So that lends itself to a larger overall equipment footprint. Next, we have evaporative condensers. So with an air-cooled condenser, we have a dry fin coil. Most evaporative condensers are going to have a smooth, larger diameter coil that's designed and optimized for wet performance. So we're spraying water directly on the coil, and as that water evaporates off the coil, that's what's driving the heat exchange for the fluid inside the coil. Evaporative condensers are going to allow you to achieve your lowest condensing temperatures, which means they will be the most energy efficient option. Also, because we're using the power of water through evaporation, we need much less surface area on the coil, so the equipment tends to have a smaller footprint. Areas of improvement or opportunities for improvement with evaporative coolers would be water efficiency. Since the coils are mostly not finned, there are fin coil options, but most of the coils for evaporative condensers will be smooth, and they're really designed for evaporative cooling. You get very little, if any, performance dry out of this type of coil, out of this type of unit. So for that reason, we're using water essentially year round. So there's definitely areas for improvement there. Also, since we're maintaining a volume of water in the basin or the sump of the unit, we need to maintain the water quality. So typically, or almost always, water treatment is going to be required. And there's a lot more maintenance tasks and activities associated with that water system. And then kind of the middle path between the two, we have adiabatic. Adiabatics can achieve condensing temperatures very similar, if not the same, as evaporative condensers, maybe not on the hottest days of the year, but they do still lend themselves to very low system energy usage. They have relatively low maintenance, still some more maintenance requirements over an air-cooled, but much less compared to an evaporative. The water use is much less than an evaporative cooler. We'll explore that later on in the presentation, but up to 90% less water use than an evaporative cooler. So that less water use means less maintenance requirements. And since water isn't maintained in the basin, the unit will drain completely at least once per day. There's no chemical water treatment required to eliminate any kind of biological growth inside the sump. Areas for improvement on an adiabatic unit. We know adiabatics represent a cost premium over air-cooled, but we also know that there is energy efficiency and operational efficiency. So of course there's a payback associated with the increased cost of that equipment, and we're always trying to reduce that ROI to make it a more viable option for more customers. And last, while it does use significantly less water than an evaporative condenser, there are customers that are always sensitive to any water use, and so we're always looking for ways that we can maximize the water efficiency and utilize that water most effectively. When it comes to what type of options you have available by your refrigerant choice, we'll start with ammonia. essentially have your pick of equipment types if you have an ammonia system. We have air-cooled ammonia condensers, adiabatic ammonia condensers. Evaporative ammonia condensers are probably the most popular. That's mostly because of the large system capacities that are typical of ammonia systems. Those large capacities lend themselves well to an evaporative cooling product. And also we have the option of going with a glycol fluid loop using a fluid cooler with the addition of a pump station and ammonia to water heat exchangers or ammonia water cooled condensers. When we look at a CO2 system, we have, of course, air-cooled gas coolers and adiabatic gas coolers or condensers, depending on how you've designed your system. And of course, there's also the option of using that glycol fluid loop with a pump station and water-cooled CO2 condensers. And then last, when we're looking at propane in terms of the natural refrigerants, most propane cases or displays are going to be self-contained, which are air-cooled. But of course, there are the options that are water cooled. So we'd have that, again, that water glycol loop with a pump station and individual heat exchangers for each case or for each rack. So now I just wanted to change gears a little bit and look more closely at what those fluid coolers or that water glycol loop cooling would look like. So what I'm referring to is we would have a water glycol solution that is in a loop that's circulated via a pump station. You would have a fluid cooler, whether it's on the roof or indoors, that's going to reject your heat. And then you have water cooled condensers or heat exchangers for each case or for each display. So in this way, it's very much like a micro distributed system. And one of the benefits of going with this type of system is that it then opens up a few more options for what your heat rejection equipment might look like. There are dry fluid coolers, adiabatic fluid coolers, and of course, evaporative fluid coolers. So I think for me, the big takeaway with this type of system is that, yes, there are additional components, namely the pump station and your water-cooled condensers, but doing so can afford some more flexibility and a system that is more easily expanded. I know with the micro-distributed type of system, using a glycol loop, it makes remodels and expansions much more feasible and with less disruption in the store. So here are 3 examples of fluid cooler projects and what that flexibility looks like for each one of these. So starting on the left, this project is using evaporative fluid coolers. It's a mixed use development, so it's a supermarket, but there are also other retail stores included in the building. And so these 2 evaporative coolers are not just handling the refrigeration load, but also some HVAC load. So it was an easy project to have the water glycol fluid loop, and then you can tap off of that loop for multiple different loads, whether refrigeration or HVAC. And in this case, the system is providing 1,350 GPM at 95 degrees entering the cooler and 85 degrees leaving the cooler. And the design is around a 78 wet bulb. Next, we have a hybrid type of fluid cooler, which I'll get into more details later, but in this case, it's a much smaller system. Only 170 GPM is required, but using this type of product allowed the unit to be installed in a loading dock and have the discharge be ducted outside. So this is just an example where maybe an indoor installation or a parking garage or a loading dock might lead you to consider a different type of equipment. And then last on the right, we have some adiabatic fluid coolers. This is a project in New York City. So the units are located high up on the roof. Typically, it's not the best idea or feasible to be piping refrigerant up multiple stories in an urban environment. So in this case, they have the glycol solution pumped up to the roof. They have two fluid coolers providing 1,200 GPM of 95 degree water entering, 85 leaving. And just in terms of footprint for evaporative versus adiabatic, here's a good visual. You've got your evaporative product on the left, you've got adiabatic on the right. They're pretty similar in terms of capacity, both around 1200, 1300 GPM, but you can see the overall installed footprint for an evaporative cooler, much more compact, much less space needed. So that is one of the benefits of evaporative. So we know with dry cooling, what we like, very low maintenance, no water is being used on site, but we're paying for that quite literally with the electric bill in operating that system. On the evaporative side, we have much higher efficiency, much higher system efficiencies, much smaller equipment footprints. But things we would like to see better would be lower water use and some easier maintenance. So if only there were a way to combine the benefits of each, right? Just a quick point on terminology as we proceed here. At BAC, we distinguish between hybrid technologies and adiabatic. So when I say hybrid, what I'm referring to is a product that can use both evaporative and dry cooling versus an adiabatic product. We are pre-cooling the air before it reaches the coil. So in an adiabatic unit, your coil or your heat exchange surface is always dry. I think that's an important distinction. So here we have a range of products with your air-cooled products starting here on the left, representing the lowest water use, but the highest energy use. And then at the other end of the spectrum, we have evaporative coolers, which are using the most water, but also using the least amount of energy. And in between, we have our adiabatic and hybrid solutions. So next to the air-cooled, we have adiabatic. It's going to be using, obviously, more water than an air-cooled, but it's the least amount of water usage compared to products that do use some water. The product in the middle is BAC's HXV hybrid cooler. I don't spend a whole lot of time talking about it today because it's really designed for larger capacity systems, more industrial type applications, not really suited for supermarkets, but it could be used on something like a cold storage ammonia plant or something like that. What's special about this unit is it includes both a dry fin coil and a wet evaporative coil in series inside the unit. So it can take advantage of both dry cooling and evaporative cooling simultaneously. And then next is a modular hybrid cooler. This unit uses a different type of heat exchanger, but can capitalize on both wet and dry performance. So why do hybrid and adiabatic technologies exist? Well, it's pretty simple. We're trying to balance the energy and water savings. We want to use water on the hottest days of the year to reduce that peak demand, reduce our peak demand electricity charges. And then in the colder months, when possible, we want to use dry cooling in order to conserve water. Not by using dry cooling periodically throughout the year, that allows us to use less water overall, which means less chemicals and reduced maintenance activities on the unit. In addition, there's inherent plume abatement with hybrid products. What I mean by plume, that's kind of the water vapor you might see billowing out of cooling towers in the colder months. Like I mentioned previously, since evaporative coolers are reliant on the water for heat rejection, even in those cooler months, we're going to be spraying water on the coil, and that's what creates that plume effect. But with hybrid and adiabatic, since we're operating dry in those shoulder and colder months, there is no plume created. That's an issue in some places, especially like New York City. It comes up quite a bit. But how do you choose which hybrid or which adiabatic product you want? Well, things to consider first and foremost are your project capacity requirements. Like I mentioned with the HXV cooler, unless you have a very large system capacity requirement, that's not going to be a viable option. So your capacity needs will help guide you to a shorter list of options to consider. From there, what's most important, your energy or your water usage? Do you want to have the most energy efficient system possible? Do you want to use as little water as possible? Or do you want something in the middle that affords you some flexibility? So those kinds of conversations and questions will help guide you one way or another. Of course, other considerations such as physical limitations for your projects, whether it's footprint or height restrictions, installed locations. I gave the example where we had a fluid cooler installed indoors. I see that a lot with mixed use development or urban applications, where we had to get creative about where to install the product. And then from a maintenance and water quality standpoint, knowing what your local service needs are and what your local water quality is like can also help guide to make a strong decision whether a hybrid or an adiabatic type of product. So what is exactly a modular hybrid cooler? Well, it's modular in that you could see here, this particular unit is 6 modules bolted together. So we have individual modules or cells. Each one operates individually, but they can be combined to make a larger unit. It's hybrid, as I mentioned, because we're using both evaporative and dry cooling capabilities. And it's a cooler because it is only available as a fluid cooler. So this type of product needs to have water or glycol as the process fluid. It's not a condenser or a direct gas cooler. So what does hybrid operation look like for this type of product? Well, of course, it can use evaporative cooling, in which in the example here, we have a 4-cell or 4-module unit. So over here on the left, all modules are operating in evaporative mode. Each module has its own spray pump. So all the spray pumps are energized and we're spraying water on the heat exchanger for all 4 units. This represents the most energy efficient operation. And then over here, all the way to the right, we have all 4 modules operating dry. There's no water being sprayed onto the heat exchanger, so it is completely dry cooler. This is when we're saving the most water. No water is being used. And then in the center, we have what we've termed as nexus mode. This is for all the other situations in between. And what's unique about this product is that each module can be staged and controlled individually. So in this case, we have 2 modules running in wet or evaporative mode and 2 modules running in dry mode. And the unit can stage on or off the pumps for additional modules as needed to meet the demand. So what does all that equal? About 50% less water usage compared to a similar evaporative cooler. So that's some pretty significant water savings while still maintaining your evaporative energy efficiency. And what is it about this product that allows us this type of operation? What affords us this flexibility? There are a lot of features on this type of unit that make it look different, but really what enables this operation is what you can't see, and that's the heat exchanger inside the unit. So instead of a traditional HVAC-R coil, this product uses a cassette type of heat exchanger. So the plates are full stainless steel, and they are robotic welded at our factory in Milford, Delaware. The plates have wide spacing in between them. So this allows a significant amount of surface area inside the heat exchanger with a low air pressure drop across it. So that's what allows us to get excellent dry performance and also very efficient evaporative performance. If we compare this type of hybrid cooler to a traditional centrifugal type of fluid cooler that a lot of us have seen at supermarkets, we can see that it's about 40% smaller footprint and even more significantly, about 5 feet shorter. This is great for indoor installations or also when sight lines or screen walls are required. 35% less weight for the same capacity. So that's significantly less in terms of your steel dunnage requirements, or if it's a retrofit opportunity, less to consider there. Where less fan and pump horsepower is required. The process fluid volume is significantly reduced. That's the volume that's flowing through the coil or through the heat exchanger, because the Nexus heat exchanger has a much smaller internal volume than a traditional coil. We can reduce that process fluid volume by quite a bit. Also, much less spray water is required and a much lower basin volume. So this lends itself to less chemical use and easier maintenance, easier dealing with that water distribution system. And then last, since the heat exchanger is standard as stainless steel, you've got an inherently corrosion resistant unit, whereas typically a conventional fluid cooler would have a hot dip galvanized carbon steel, a copper, or maybe a stainless steel coil as well. But those would all be price upgrades from the standard. Whereas with this design, you've got a stainless steel heat exchanger out of the box. So there are some additional components and complexities to this type of product, but the intent is to make it easier to design, install, and maintain. The fact that we have multiple modules that can be bundled together and still with only a single inlet and outlet connection means we have great redundancy without the complexity of piping multiple units in parallel. The very compact nature of it means it can be installed indoors or outdoors. There's a lot of flexibility with its mounting locations. Low weight means less structural steel, and low height means lower screen walls when they are required. The units do come with full factory controls, so you don't have to worry about a controls provider coming up with this sequence of staging the spray pumps. It's all built into the unit as standard. The sump or the recirculating water basin will come from the factory with piping connections with taps to connect your chemical water treatment system. Again, since this is an evaporative cooler and water is maintained in that basin, chemical water treatment would be needed to maintain water quality. And we provide those connections right on the basin for easy system integration. And last, again, leading to its compact nature, each individual module can be handled with a pallet jack. So even if we have a 6-module unit, the modules can be shipped individually and handled on site without the need for a crane. That's going to lead us next into our adiabatic products, adiabatic condensers and fluid coolers. So adiabatics can offer up to 90% water savings versus a comparative evaporative product. 50% more energy efficient than an air-cooled system. With an adiabatic, since the coil is completely dry 100% of the time, there is zero plume to worry about. And there are features most adiabatic manufacturers have included to help lower maintenance. Units that use a recirculating water pump have a daily purge included in the sequence. So once per day, typically overnight, the small volume of the sump in an adiabatic cooler is going to drain completely. It will run dry overnight. So that eliminates any need for chemical dosing of that sump. Also, we find that the pads for adiabatic type products act kind of as a filter or a sacrificial barrier for the coils. So typical maintenance for an air-cooled condenser would involve cleaning the coils. And we find with adiabatics, coil cleaning may not always be required because those pads are filtering out a lot of dirt and debris before it reaches the coil. The units have a self-clean cycle built in. So overnight, when your case loads are low, the fans will actually run in reverse and try to dislodge and blow off some of that dirt and debris that's been collected on the pads. When it comes to adiabatic products, they can be applied really for any application. They're available with stainless steel coils for ammonia applications. They're available with high pressure CO2 coils, so we can have direct CO2 condensing or gas cooling. And they're also available with water glycol coils. So we do quite a bit of adiabatic fluid coolers as well. Adiabatic products have two basic modes of operation. There's dry mode. This essentially, the unit is acting just like a dry cooler. That's when the ambient outdoor air temperature is below whatever the design switch point is. No water is being used, and you have maximum energy savings. This is typically during the colder months, 70 degrees and below. Once the ambient temperature reaches our design switch point, the unit switches into pre-cooler or adiabatic mode. Water is distributed over the pads and air is cooled as it is drawn across the pads. So we can typically cool the air to within 1 or 3 degrees of the ambient wet bulb temperature. So this is what allows us those lower condensing temperatures, those lower outlet gas temperatures. When in pre-cooler mode, that's when you're maximizing the energy savings for your system. So we're going to get into a little bit what's happening to the air during that adiabatic process. So just a point of reference, sensible cooling is when we're just raising or lowering the temperature of a substance, very much akin to transcritical CO2. When we have transcritical operation, we're just sensibly cooling the CO2. Whereas latent heating or cooling, that's the energy needed to trigger a phase change. Again, similar to with subcritical operation in CO2, when we're able to actually condense the CO2, we have latent cooling, much higher cooling effect. But now we're going to talk about not what's happening in the coil, but what's happening to the air as it's moving across that adiabatic pad. So in this example, the red dot represents air at 100 degrees dry bulb, 78 wet bulb. When the adiabatic product is in dry mode, the air, there's no water being used, the pads are dry. So the 100-degree ambient air is the same 100-degree ambient air you have reaching your coil. Once pre-cooler mode is activated, as water is distributed over the pad, as air is pulled across the pad, it's going to follow this orange line. The energy it takes to evaporate water off the pad is absorbed from the air in terms of its sensible heat. So the air temperature is being reduced, it's giving up sensible heat, and in return, it's picking up latent heat that was needed to evaporate the water. And that's what an adiabatic process means. The definition of adiabatic is total enthalpy is conserved. So everything that the air gives up in terms of sensible, it is gaining an equal amount of energy in terms of latent. And if we had a 100% ideal cooler, we would be able to cool the air all the way to the saturation line or 78 wet bulb. Of course, no such mechanical equipment exists. So if we assume a 93% saturation efficiency, we can actually cool that air to within about 79 degrees. So that's a pretty significant drop in the air temperature that's reaching your coil. And again, that's what allows us to get those lower gas outlet temperatures, lower fluid outlets, and lower condensing temperatures. So depressed dry bulb temperature, that refers to the air temperature after the pads, how much we're able to cool the ambient air. And it's directly related to both saturation efficiency and the ambient conditions, as you can see from the simple equation. This equation also easily demonstrates why adiabatic is not as effective in very humid climates. When there's a small difference between the dry bulb and the wet bulb, which is what humid climates would be, when there's a small difference between the two, that significantly limits our ability to create depressed dry bulb temperature. So there's not as much delta there to be had. And then, of course, it's also related to the saturation efficiency, which is dependent on choices that the equipment manufacturer makes, things like pad thickness, the amount of water being flowed over the pad, airflow, face velocity, things like that. So for a given product, your saturation efficiency is a constant, and the ambient air conditions will vary. So let's take a look at adiabatic versus air-cooled in terms of payback. Here we've created a matrix. We have 3 different climates, dry, standard, and humid climates, and 3 different system sizes, 800 MBH for a small size, 2500 MBH medium, and a large system at 4000 MBH. And we've color-coded the simple payback or return on investment. And so we see that we get the fastest payback, of course, in dry climates and higher tonnage ranges versus air-cooled condensers. In humid climates, adiabatic can still work, but just be prepared that that the payback, the ROI, will be a little bit extended versus in a dry climate. Besides just the payback, what other considerations are important if you were going to go with an adiabatic? Some locations just have very high energy costs. I'm thinking places like the Northeast, high demand charges, high electric cost, that might push you more towards an adiabatic. Also, if you have space constraints, your adiabatic product will be a smaller footprint than a comparable air-cooled. And also, if you have sound restrictions, because we're using water through the adiabatic process, that means we need less airflow to make the same capacity. So your adiabatic product will have lower sound levels compared to an air-cooled. And let's see what that looks like with some actual equipment numbers. So here we're using the medium-sized system, 2,500 MBH in a dry climate as an example. 50% smaller footprint for an adiabatic product compared to a comparable air-cooled. Your annual energy use, which is a combination of not just the condensers, but also the compressor rack consumption, 15% less energy in this case. The dry switch point of 77.7. So this adiabatic cooler can operate completely dry if need be, up to almost 78 degrees. You could, of course, design the switch point to be lower than that if you wanted to use water more and capitalize on some energy efficiency. Most adiabatic products, most manufacturers have premium materials of construction as standard, things like powder-coated panels, stainless steel coils, corrosion-resistant coated coils. So your adiabatic product is generally corrosion-resistant as a standard, whereas with an air-cooled condenser, those are all additional options that you would have to add on. And then, of course, your sound levels. In this particular case, up to 8 dB lower in sound levels. So now let's go through the same analysis or same comparison with adiabatic versus evaporative. Again, we have our three different climates: dry, standard, and humid. Our three different system sizes: small, medium, and large. So versus evaporative, again, we see the shortest payback is in dry climates, but more so on the smaller capacity ranges. With evaporative cooling, we're getting much more heat rejection out of a smaller piece of equipment. So larger systems, larger capacities are going to lend themselves more to an evaporative product. But other considerations that might lead you away from evaporative to adiabatic might be local water scarcity or local codes or restrictions on water use. When it comes to ammonia systems, the coils in an adiabatic unit have much less volume than a comparable evaporative, so we can reduce the charge and possibly eliminate some PSM requirements. And then, of course, the weight. Since we have much less water in suspension and in the basin of the adiabatic unit, the weight is going to be significantly less. So this is important, again, for retrofit opportunities or if structural steel needs to be designed. So again, comparing an actual equipment selection, again, we're at that medium capacity range in the dry climate conditions. The adiabatic product is a larger footprint, but it is 4 feet shorter, and that's pretty common when comparing adiabatic and evaporative. You'll find that adiabatic units tend to be shorter. The operating weight, 25% lighter in this case, and the refrigerant charge is 30% reduced. In this case, we're using 80% less water than the evaporative condenser. And as I mentioned before, this evaporative condenser dry switch point 1 degree F. So we're really not getting any type of dry cooling out of it. Whereas with the adiabatic product, we're able to operate dry all the way up to 71 degrees. And then again, the note about materials of construction: most evaporative condensers are going to be galvanized steel. There are options to upgrade to full stainless steel, whereas your adiabatic units are going to be corrosion resistant premium materials as a standard. And for this particular case, again, lower sound levels using the whisper quiet axial fans on a adiabatic condenser. So just to summarize all that into one slide, versus an air-cooled, your adiabatic products will offer System energy efficiency, your compressors will operate much less. You'll have lower electric bills, lower sound, reduced footprint, and a lower total cost of ownership, meaning that there is a payback associated with purchasing adiabatic versus air-cooled. Versus evaporative, we're going to save considerable amounts of water. We're going to reduce the maintenance requirements and chemical water treatment that is needed for an evaporative, and also reduce total cost of ownership in terms of saving on maintenance. So we've established this spectrum or this range of products from evaporative, hybrid, and adiabatic. And now I'm just going to explore a little bit the trade-off between energy and water use. So evaporative cooling products, or even hybrid or adiabatic products, use water in three ways. And I'm just talking about the water use contained within the unit. The first is obviously through evaporation. That's what's driving the heat exchange, so water is being evaporated. The second is blowdown or bleed. As water is evaporated out of the system, the minerals and dissolved solids from the domestic makeup water will stay behind in the sump or the basin. And so as water is continuously evaporated, the concentration of those minerals is going to begin to build up in the sump. And so we need to periodically purge some of that water and make up with fresh water to control that concentration. That's another source of water use. And the third, which is not very significant, is drift. And this is water droplets that are physically escaping the unit. Not much of a concern with adiabatic, more so of a concern with evaporative type products. Even then, so the loss is a fraction of a percent. Products and features like drift eliminators can help trap the water and keep it inside the unit. So here, let's look at evaporative, hybrid, and adiabatic in terms of water use. So starting on the left, this was modeled first with BAC's FXV closed circuit cooling. So it's essentially an evaporative fluid cooler that's used as the baseline. Next, we see the Nexus modular hybrid cooler. This is the unit with the cassette heat exchanger. It can operate both wet and dry. So we see that type of operation allows us to reduce water consumption by 50%. Next, we have the HXV hybrid cooler. This was the larger product that has both dry fin coil and wet evaporative coil in series. Since we have that dry fin coil, we're able to get essentially free sensible cooling before the process fluid goes to the evaporative cooling. So that enables us to significantly reduce the amount of water that's needed to spray on that wet coil. So we see a 70% reduction for an HXV in water use. And then last, adiabatic. Again, since we're not spraying water on the coil, we're only using water to wet the pads to pre-cool the air. We can expect a 90% water savings. And again, just to keep everyone grounded, as we save water, we're giving up some energy efficiency. There is a trade-off between the two. Next, I wanted to talk a little bit about your design switch point when it comes to adiabatic. So here we have an example in Indianapolis area. Here's my design conditions. We've got a rack around 800 MBH, and it's using a 4-fan CO2 condenser. The outlet temperature is 85, so it is designed for subcritical operation. So here we vary the switch point from 75 to 78, 80, and 82. So this is the temperature, this is the ambient temperature at which the unit is going to activate the water and go into adiabatic mode. We see the water use through both evaporation and bleed rate. So as we increase the switch point, that means there's going to be less operating hours in wet mode. So less operating hours means there's going to be less water evaporated, and there'll be less of a need for blowdown or bleed rate. And so we can see that in the overall water consumption values. And then we also see the energy consumption related with each design point. Energy consumption is both the gas cooler and the compressor energy. If we look, if you look a little bit more closely at the two extremes, 75 switch point and 82 switch point, and put some dollar values on what the operational cost would be, we can see that even though with the 75 switch point, we're using nearly 3 times as much water, from a dollars and cents standpoint, if you're just looking at your operational expenses, it's still better to use the water and save on the energy efficiency. Of course, there are other considerations beyond just the dollars and cents of the financials, and for that reason, that's what's great about adiabatic products is that the switch point is user defined, it is field adjustable, so you can fine tune the system, fine tune the unit to meet the needs and meet the requirements for your specific company or your specific project. Here's one more example. This one is using a fluid cooler application. So again, it's showing us pretty much the same thing, just a different application. The prior one being CO2, this one being a fluid cooler. If we vary the switch point from a very high switch point of nearly 82 degrees down to 50 degrees, we can see that the energy costs will be reduced significantly. And yes, the water costs do go up, but still the net expenses would favor a lower switch point and a more energy efficient system. So I probably could have saved all this time and just had one slide. I think this is an excellent representation of the message I've tried to convey today. These dots represent your different product types, from a dry cooler, adiabatic, your hybrids, and your evaporative. The dot size represents the unit footprint. So we can see a relative size of the equipment for a given capacity. And our y-axis is energy use. Our x is water use. And so we can see dry coolers would be larger footprint, highest energy use, lowest water use, while also considering your gas outlet temperature, condensing temperature, or process fluid outlet. We can see as we use the adiabatic, hybrid, and evaporative technologies, that allows us to get colder temperatures, which is directly related to that more efficient operation. So that's all the topics that I had to cover. I would encourage anyone to ask any questions. Also, anyone listening now or listening recorded, feel free to reach out to me, either phone or email. Be happy to answer any questions that may come up after.